Ask questions when you get confused, not 15 minutes after, because this stuff is really builds on itself. Make sure you get one term and one relationship before we go to the next one. If you have a question, I can guarantee you somebody else has the same question. Okay, so here we go. First off, let's talk about the big picture physiological design of the cardiovascular system. The big picture physiological design of the cardiovascular system is plumbing, right? And plumbing works on pressure to produce flow. You with me so far? And what opposes flow is something called resistance. Now, what is all the plumbing serving? All of the plumbing is serving the capillary beds. So here's the deal, and I need you guys to understand this. The ultimate physiological function of the cardiovascular system is to deliver adequate blood flow to capillary beds. And you will try to do that even if you trash the system in the process. Because if you don't deliver adequate blood flow to capillary beds, you are going to die, right? So in situations like this, how does it possibly make sense that if I have arteriosclerosis and my blood pressure is really high, then my freaking heart rate increases? How could that possibly make sense? It does make sense because if I've got arteriosclerosis, I am not delivering adequate blood flow to capillary beds. And so what's my heart going to try to do to help? It's going to increase. It's still going to trash the system more, right? Because you're going to increase the pressure more. But remember that if you are controlling multiple functionalities, the trump is always delivering adequate blood flow to capillary beds. The trump part, right? That one always wins, even if you trash the pump and the tubes in the process. Because the pumps and the tubes wouldn't be a damn thing if you couldn't deliver adequate blood flow to, for instance, your brain, right? Then the plumbing doesn't matter, okay? So that's the one thing that always wins, even if it's slightly counterintuitive. Okay, so here's the deal. Blood moves like all fluids move. The flow is due to pressure, yes, okay? And the pressure is primarily created by the pumping of the heart, yes? You can augment it, add to it, or subtract from it by how much fluid is in there, like your kidneys can add to or subtract from the pressure. And you can add to or subtract from the pressure by vasoconstriction or vasodilation, but the pressure is generated by the pumping of the heart. Good? Okay, and we're going to do that in more detail today. So you guys predict for me before we get into the details. Your prediction is as pressure increases, flow tends to do what? Increase, yes. Until pressure gets too high. Pressure can be too high for flow. You can bust the damn thing if the pressure is too high, right? So there is this nice sweet spot for pressure, and then there's too high, and then there's too low, right? And flow is opposed by something that we call resistance, okay? So pressure favors flow, resistance opposes flow. Resistance is primarily due to friction. So I want you to think about pressure as occurring all through the system. Resistance actually really occurs in the vessels. It doesn't really occur in the heart. Anything that increases friction in the vessels, like for instance, decreasing the size of the tube, that'll add to resistance and therefore do what to flow? Decrease flow, okay? Or gunking up the tubes with arteriosclerosis or atherosclerosis, or getting longer tubes. They have more friction, right? Longer tubes, right? Or how about increasing the viscosity of the fluid? If your blood becomes really viscous like maple syrup, right? Doesn't that increase the resistance? Okay. So we've got the pressure and resistance that are sort of opposing one another. So flow is opposed by, we call it peripheral resistance because it doesn't occur in the heart, right? It's in the periphery. As resistance increases, flow tends to do what? Decrease. Resistance occurs primarily in the vessels, and we'll talk about it today. Okay, so why do the capillaries get all of the service? Well, because gas exchange only occurs in the capillaries, right? They are the only ones that are thin enough and branched enough that you actually can get oxygen out, nutrients out of the capillaries, and waste products and carbon dioxide back into the capillaries. So all cells in the body are within a few centimeters of a capillary, and the more active a tissue it is, the more capillaries it will have in the tissue. And of course, if we're talking about systemic circulation, and please assume today that we're going to talk about systemic circulation unless I specifically say pulmonary circulation, okay? Pulmonary is important. It doesn't go bad as often. So, of course, your capillaries, you know what they're doing in systemic circulation. they're bringing nutrients and oxygen to the tissue, and they're taking away carbon dioxide and waste products from the tissue. Okay, so first thing before we get into the details is just how do the oxygen and nutrients get from the capillaries into like the tissues and the tissue cells? Cheapest, fastest way they can, right? That's the rule that we learned. So if it's oxygen, it's lipid soluble, and it just moves straight into the cells down its concentration gradient, right? If it's not lipid soluble, then I promise you'll have a transport mechanism for it if it's important, right? Like for instance, glucose. Either the capillary is fenestrated so you can get it out, and then the cells, of course, are going to have glucose transport mechanism on them, right? In the brain, the capillaries are definitely not fenestrated, but you have glucose transport on both the capillaries and the cells. That makes sense? So if you need it, it's either soluble or you'll have a transport mechanism for it. And the transport mechanism is going to be as cheap as you can possibly move it, right? Okay, so also, when you move nutrients and oxygen out, because there's a pressure difference between blood plasma pressure and interstitial fluid pressure, you always do filtration at capillaries. Which fluid is higher pressure, blood plasma or interstitial fluid? Which one has a pump behind it? Blood plasma, right? And since blood plasma is higher pressure, you're always going to do filtration at capillaries, which means in addition to the solutes you move out, you always move water out. Yes? That's where your interstitial fluid came from, guys. It was actually blood plasma in its past, right? Okay, so you're always losing fluid into the interstitial fluid, and then you pick most of it back up by osmosis, and whatever you don't pick up back up by osmosis, you pick up back into the lymphatic system. And this simply means that you actually have a turnover of interstitial fluid, right? Pushing it out by filtration, pulling it back up by osmosis, pushing it out by filtration, pulling it back up by osmosis, okay? So you do have turnover of interstitial fluid. All right, so now, ooh, spider. Why are we so spidery? Okay, so now we're gonna talk about how circulation works. It is this interaction that we just talked about pressure, flow, and resistance. And so the equation that we're going to be dealing with is super easy. F is blood flow, which is what we want. Specifically, we want blood flow to capillary beds. And F equals delta P over R. Okay, so let's talk about what that means. Flow, which can be measured in any unit of volume per unit of time, right? So we're measuring the speed of blood flow, and we'll do it in liters per minute or sometimes milliliters per minute, is delta P over R. P is pressure, but it's really not pressure that makes blood flow, it's difference in pressure. Okay, so if I had pressure of 120 millimeters of mercury in a tube at this point, and 120 at this point, I get zero pressure. I get zero flow, right? I can double it and still get zero flow. I can halve it and still get zero flow. So the real reason that blood flows is because of a difference in pressure between 2 points. Here's P1 and here's P2, right? Does that make sense? Okay, so which direction is blood going to flow? That direction, and it will flow at different speeds depending on the magnitude of delta P, correct? Right? Now you still know the direction, but you know inherently that the speed is going to be different, right? It's not going to be that hard to understand. So this is basically plumbing. So let's put it back to 70. So the important thing is pressure. Blood flows from high pressure to low pressure. I'm not opening that. I can walk around. Okay, blood flows from high pressure to low pressure. So let's look at a couple of different situations. No, walk around. Who raised you? Huh? The barn. Okay, here's the deal. So look at these situations. Okay, look at these situations. I am not, this is now.
It's not principle of the thing.
It's the principle, right? Okay, so now let's look at these situations. You ready? Okay, so we've got two different pressures, right? We've got two different pressures. We've got 100 to 60. What? I'm going to open it. You need to walk around next time.
Oh,
Yeah. If you're going to do that, you have to be on time.
sorry.
Okay, so I have two different pressure situations. Notice that the delta P here is 40, and they set the resistance at 2, just arbitrarily. And that gets you a flow of 20 milliliters per minute. Everybody okay with that? Okay. Notice that in this situation, you have way higher pressure, but the same delta P, right? And the same flow. So this is a healthy person, for instance, and this is a person with hypertension. Because if P2 increases, what do you have to do to P1 to maintain the flow? Does that make sense to you? So this bottom situation is a situation in which P2, maybe the pressure in the arteries, has increased because of vasoconstriction and arteriosclerosis. Good, right? But you still need blood flow to your capillary bed. So what do you have to do with the pressure that is generated by your heart? You have to generate way more pressure to have the same flow. Does that make sense? And please note that if you get into a situation in which you have no pressure difference, like your heart is not pumping, you ain't got no flow, right? You ain't got no, right? That makes sense? Okay, so we're going to talk about hypertension. Do you see how this might be a hypertension situation? You're trying to maintain the same damn flow. You just have to do it at way higher pressures. Okay, so let's talk. It is the difference in pressure between 2 points. So it's not really P that makes flow, it's delta P that makes flow, yeah? So it's the difference in pressure between 2 points that determines both the direction and also the velocity of flow. Yes? That make sense to you guys? Okay, so flow is, do you know the terms directly proportional and inversely proportional? Okay, directly proportional simply means as one increases, the other increases, and inversely proportional means as one increases, the other decreases. So flow is directly proportional to the difference in pressure between 2 points, or as pressure difference increases, flow does what? Increases. Good. Okay, so now let's go back and say, hey, how do you manipulate pressure in the human body? And this is going to stay consistent for the rest of the semester and for the rest of your damn life. How do you manipulate pressure in the human body? Blood pressure. You manipulate pressure 3 different ways. Pressure is generated by cardiac muscle contraction, right? So if you do anything to cardiac muscle contraction, you can change pressure. But it can be augmented or decreased by 2 other ways. It can be augmented or decreased by blood volume changes, which would primarily occur where? Kidneys, yeah. So the kidneys can dramatically impact. Hopefully that makes sense. I've got the same set of tubes. Now I'm going to put more fluid in it, the pressure increases, right? Okay. And the other way that you can do it is you can augment or decrease the pressure by changing the diameter of the tubes. Yes? So I've got a system, I've got a constant pressure being generated by the cardiac muscle, I've got a constant volume, and now all I do is systemically vasoconstrict. What happens to pressure in the system? Goes up, systemically vasodilate, the pressure goes down. That make sense? So really what I have is one source of pressure and 2 ways to manipulate it after I've created it. Good? Okay, now you will see that throughout the rest of the semester, no matter what you are trying to do to blood pressure, there's only 3 ways to do it. You do something to your kidneys, something to your heart, or something to your vessels, right? It'll be consistent. Okay, so now pressure is measured in millimeters of mercury. Okay, you guys know that that's how you measure barometric pressure and blood pressure and everything. Okay, now let's look at what happens with the magnitude of the pressure. So I want unidirectional flow through a circuit, don't I? A cardiovascular circuit. Don't I want in the systemic circuit to go from the left ventricle, which is where it starts, right, to the arteries and then arterioles, right, and then capillaries, venules, veins back to the right atrium. If I want unidirectional flow, does it make sense that you better have a pressure gradient that goes all the way through? Yeah? Okay, so let's look at the average pressure as you go through the circuit, and then we'll also look at pulmonary circuit real quick. So this is just average pressure as you go through. Notice that the arteries are way higher than the arterioles, drops dramatically in the capillaries, drops again in the venules, drops in the veins. It's actually almost 0 millimeters of mercury in the right atrium. So it goes from a little bit above 120 at rest in the left ventricle all the way back to 0. And since you have that pressure gradient, then you get unidirectional flow. Now, would you be screwed if the pressure really dramatically increased in your veins? Yeah, you can make the blood go backwards. If you make it go backwards, it's going to leak out of the capillaries if you screw up the pressure that side. Now, notice that the pulmonary circuit also has a pressure gradient, but it's a much, much lower number pressure gradient. Now, I know you know this, but I want you to verbalize it. What anatomically is responsible for the difference in the magnitude of pressure in the systemic circuit versus the pulmonary circuit? What is it anatomically that is responsible for the difference in pressure between those two circuits? Nope. Size of, yeah, the size of what? The ventricle, the muscle in the ventricle?
Yeah.
So the left ventricle is way thicker and stronger and can generate way more pressure, right, than the right ventricle. Now, and then also, of course, it needs to, right? Because the right ventricle is just going heart to lungs, right? And the left ventricle is going heart down to little toe all the way up to brain, right? So the left ventricle works at way higher pressures. Can you see now just a little bit of a prediction why if we have cardiovascular problems, they are far more likely to be systemic cardiovascular problems than pulmonary? I mean, pulmonary do occur, but if you're talking about stats, and if we're talking about someone, saying, hey, I've got hypertension, right? Are they talking about systemic or pulmonary hypertension? Yeah, right? We've got more tubes, right? We're dealing with higher pressure. And which system is more likely to wear out on you? Systemic, yeah, that's the one. It's dealing with way higher pressure. Okay, now, this is average pressures through the system. Now let's take a few more data points and look at actual pressures. Okay, this is just systemic. So not only is pressure higher in the arteries, it's also more variable in the arteries. And that shouldn't be at all unfamiliar to you. Okay, so if we look at arterial pressure, what we see is, of course, there's a difference in systolic arterial pressure and diastolic arterial pressure. And you guys did this in lab. The systolic arterial pressure is the pressure immediately after ventricular systole or contraction, right? And so it goes up pretty high, maybe 120, right? And the diastolic is at the end of diastole right before the next systole. That's as low as it ever gets, right? So it goes systolic, diastolic, diastolic. So if you assessed an artery, a systemic artery, you'd have a pulse pressure in it, right? But please notice that the pulse pressure gets pretty minimal in arterioles. You lose it completely in capillaries. And do you have a detectable pulse pressure in your veins? No. And if you nicked a vein, would the blood go squirt, squirt, squirt? No, it'd go trickle. If you nicked an artery, what's going to happen? Squirt, squirt, squirt. Yes, exactly. Okay, don't do that. Okay? Okay. Does that make sense to you? So that's systole and diastole. Okay. So the blood pressure is going to be manipulated, like I said, by blood volume, cardiac output, and also vessel diameter. So now what we're going to do is we're going to talk about the R. Okay, we figured out the delta P, and we will talk about pressure quite a bit more in the future, but we figured out the big picture of delta P. And remind me, if I was going to manipulate my blood pressure because I wanted more blood flow, there are 3 ways for me to do it. What are they? Cardiac, heart, kidneys, vessels. Good, you got it. Okay, now this one is a little harder to understand, but the regulatory mechanism is just one way. Okay, so this is called peripheral resistance, guys. Okay, so what I want to talk about now is I'm holding these 2 numbers constant, and I can change flow, F, dramatically by impacting friction between the 2 points. Does that make sense? Okay. So I can decrease the diameter, I can gunk it up, I can make the fluid more viscous, yes? Okay? Or I could make the distance between P1 and P2 way longer, okay? So let's talk about peripheral resistance. So resistance really happens in the periphery or the tubes. It doesn't really happen in the heart, which is nice and wide open. Okay, so flow is inversely proportional to the resistance between 2 points. Or as resistance increases, flow does what? Decreases, of course. So friction is the primary consideration in determining resistance, and most of it occurs in the vessels, not the heart. So what factors impact resistance and friction and therefore resistance? Well, the first one is viscosity of the fluid. So what I want you to imagine is I'm going to hold this tube a constant length, and I'm going to try to get whole milk to go through a 6-inch tube by blowing it. Pressure, right? Okay. And you blow it, and it goes through. And now I'm going to try to blow maple syrup through the same tube. Will I be able to get it to go at the same pressure? No, because the resistance is way greater, right? That's the viscosity of the fluid. Now, what impacts viscosity in human blood? Well, it doesn't change daily in most of us. It has to be pretty dramatic. Usually it's patho situations, but not always. Okay, so if you became super duper dehydrated, can you see that the viscosity of your blood would change and therefore it would be harder to pump? Yeah, super dehydrated. Or your hematocrit changed. The hematocrit is the proportion of dissolved, or not, the proportion of solids in your blood, like leukemia. One of the things that happens with leukemia is, okay, I've got bone cancer, and with leukemia, what tends to happen is you produce a whole bunch of immature white blood cells, yeah, and you dump them in. They're not doing a damn thing. They don't even function properly. You're just making a ton of them. So it's a terrible irony that you got more white blood cells than ever, and your immune system is completely trashed. So the hematocrit in a person with leukemia, the solids are really, really high, and their blood is really thick and viscous and hard to pump. And so it can actually cause heart attacks and strokes and pulmonary embolisms. In addition, one of the first indications, sometimes with males with leukemia, is because of the viscosity of the blood, it actually causes a priapism. Do you guys know what a priapism? It's an erection long past the point that you wanted one. So the blood actually gets so stuck in the vessels of the penis that you have like a 3-day erection. I mean, nobody wants a 3-day erection, right? So, and sometimes they actually have to go in and drain it. So, priapism. Okay, so it changes with dehydration, changes with the hematocrit. It's relatively constant in a healthy individual. Do you have somebody who's blood doping? Sometimes that's the reason they die, is because they shoot themselves up with so many blood cells or so much EPO that they have such viscous blood that they have a heart attack. Okay, so the other one is vessel length. Okay, so if P1 and P2 get really, really far away from one another, I am going to try to blow the same volume of fluid through a 6-inch tube and now through a 60-inch tube. Is the same pressure going to be adequate? No, because of friction in the tube. Okay, so this is important in a couple of different times. So first of all, when I'm growing from a little baby to an adult person, of course I need to have more vessels, which are going to have more friction, but of course the size of the pump increases at the same time, right? So it's generally not problematic as you're growing. When it becomes problematic is when you're an adult, size of your heart is relatively limited. If it gets bigger, it's generally not a good thing. So let's say your heart is staying a relatively constant size, and then you get pregnant, right? So if you get pregnant, you're going to gain, I don't know, between 25 pounds, and I've got a friend who's 5'1", and every single time she gets pregnant, which is like 7 times now, she gains 100 pounds. So what happens to the blood pressure if you have more vessels? If you gain weight, whether it's pregnancy or obesity, you make more vessels, yes? You do angiogenesis. And because you have more vessels, what has to happen in order to get the blood to places is your pressure has to get higher, yes? Now with pregnancy, it's going to go away, right? You're going to give birth to that damn thing, right? But with obesity, it doesn't go away. So one of the things that is associated with obesity, just because of the physics of more tissue, is that you are going to have higher blood pressure. Does it mean you'll necessarily have hypertension? No. It means that your blood pressure is higher than it would be if you were not obese. So what is the first thing that they tell you when you start having hypertension and you're overweight? Lose weight. Yeah, go ahead.
Does that relate to varicose veins at all?
Varicose veins are primarily genetic. Obesity adds to it just because it adds to the pressure that you are pushing against, and it makes the valves more likely to balloon out. But you just have certain amounts of collagen in the walls of your vessels based on your genetics and then also your behavior. If you stand around a long time, you get varicose veins too. Did somebody have another question? I thought I saw another. Go ahead.
How does that work in somebody that loses large amounts of weight?
Well, the phenomenal thing is that although you do not actually lose all of your fat cells, as a matter of fact, you don't lose very many of your fat cells at all when you lose weight. What you do is you lose a bunch of the capillaries because you've got less tissue. So you can do angiogenesis to feed it, and then the capillaries will atrophy later. So you'll still have the fat cells, you'll still have more capillaries than you did before, but you are going to reduce it dramatically. And therefore your blood pressure really, really can drop, right? It can drop and still deliver adequate blood flow to capillary beds. So that's just a physics thing. I don't know why they don't ever teach that, because it lets you know exactly, you know. Of course, the other reason that your blood pressure tends to be a little higher when you're obese, not pregnant, but obese, is that a lot of us, you don't get obese by eating, you know, carrots and celery. You generally have arteriosclerosis and atherosclerosis simultaneously, right? So then you also reduce your lumen size. Does that make sense to you? Okay, so now vessel length doesn't change dramatically from day to day. The thing that does change, and the thing that we use as a regulatory mechanism for resistance, is vasoconstriction and vasodilation. Does that make sense? So let's talk, before we get to vasoconstriction and vasodilation, about just inherent vessel diameter. So I want you guys to think for a second. Don't think about vasoconstriction and vasodilation yet. Just think about comparing the size of the aorta to the brachial artery, okay? And tell me what the general trend is. A larger tube will have less resistance and therefore what flow? Increased flow. Right? That makes sense? Aorta, does it have more flow than the brachial artery? Yes. Okay. Increased flow. Okay. That makes sense? Okay. So can you get too big to have good flow? Yeah, if you are a stream and you've got good flow but you become a lake, what happens is you compromise the pressure. Right? So there's a sweet spot. There's like big enough and then there's too damn big. You drop the pressure. Good? Okay. Now, a smaller tube, the brachial artery, has more resistance and therefore what flow? Decreased flow. Okay. That's just like, okay, I want to water my garden, right? I could use a hose that was that big if I had all damn day, right? Or I could use a hose that was that big, right? Does that make sense? Okay. So now, just that's inherent vessel diameter, right? And now I want to talk about vasoconstriction and vasodilation. But there are two different ways to think about it, and I really need you to listen to this part because it confuses the living hell out of people if they lose it right here. Okay, so I'm going to talk about vasoconstriction and vasodilation first as regional, short-term vasoconstriction and vasodilation of arterioles. Okay, so here's what I want you guys to imagine. You guys are the liver capillaries. Yeah? I am the arteriole that is controlling flow to you. I've got a control problem, right? So I want to control everything. I want to control exactly what you get. Okay, so in certain situations you want to increase the flow, and in certain situations you want to decrease the flow. This is controlled by paracrine agents primarily. We are not talking about control by the nervous system or the endocrine system. We're talking about local control, right? Okay, so now I want to tell you one little situation. Let's say a tiger walked into the room. Do we really want to send a whole bunch of blood to the liver when a tiger's in the room? So what am I going to do? I'm going to vasoconstrict, increase resistance, decrease flow to you. Yes? Does that make sense? Okay, so that's the first one. If arterioles constrict before a capillary bed, it decreases flow to that organ. Now, could it have an impact on blood pressure? It could, but that's not the point, right? Does that make sense? I'm not trying to do local vasoconstriction to have a blood pressure impact. Could it be a detectable little bitty change? Could, but that's not the point. You okay with that? Okay. What I'm trying to do is manipulate resistance. You can have a secondary impact on pressure, but that wasn't the real point. Okay, you with me? Okay. Now you guys, no tiger in the room. Okay. And last night you did 3 tequila shots, and because you didn't listen to me the first time, you took acetaminophen to avoid a hangover. Now, tell me about your blood flow needs in the liver. It needs it. So what do I need to do? You guys say, I need blood. I make poor decisions. And you send some paracrine agents my way. And then I do vasodilation, right? I vasodilate. It's a regional, short-term thing. And in that situation, if arterioles dilate before a capillary bed, it does what to flow to that organ? Increases blood flow to that organ. Okay, now I want you to go ahead.
How are paracrine agents going your way if the blood is going our way?
Paracrine agents just diffuse.
No, they just
Diffuse into the tissue.
Right.
They're not bloodborne. Is that okay? Go ahead.
Yeah, silly question.
Okay, I mind.
You brought up the tiger.
Uh-huh.
How come some people piss themselves on his hip?
Oh, you lose control of your voluntary sphincter at the bottom.
Okay.
Your skeletal muscle sphincter. Right? Does that make sense? And you don't actually pee like everything in your bladder. You pee what was between the internal and the external urethral sphincter.
So they over-embellish in the movies then?
Yeah, they do. I mean, it's what your dog does, right? When he gets super excited to see you, he doesn't like pee all of his bladder. He like squirt, squirt, squirt. Right? Yeah? Does that make sense? So the internal sphincter is smooth muscle, and the external sphincter is skeletal muscle. And if you're super busy, right, being super excited because your master's home, or you just got into a car accident, or there's a freaking tiger, you're like, I'm thinking about staying alive. I forgot to contract my skeletal muscle sphincter. You're keeping that thing contracted right now, and we all appreciate it. Okay, so I want to give you one caveat, and I want you to listen to this because you're going to see it again later, and you're going to hate it if you didn't listen right now. Okay, there are two different reasons to do vasoconstriction and vasodilation. Okay, the one that we just saw was basically using vasoconstriction and vasodilation to manipulate resistance and therefore flow. You with me? Okay, and that's regional. That is short term, it's local, it's all paraffin-related. There's another reason to do vasoconstriction and vasodilation, but this one is systemic. It's doing the whole body system at one time, and it's really to manipulate pressure. So here's what I want you to imagine. I'm super allergic to peanuts, I'm not, but I just ate a peanut, and I go into anaphylactic shock, and I have massive vasodilation. You guys with me? Okay. Now, what I need to do is I need to do massive vasoconstriction, but this time I am not trying to do vasoconstriction to decrease flow. I'm doing massive systemic vasoconstriction to increase pressure. Yes? Does that make sense? Okay, so there is a difference between systemic vasoconstriction, which is generally used to manipulate pressure, and local vasoconstriction, which is generally used to increase resistance and decrease flow. Does that make sense? Just depends on where you're doing it and why. If you do it systemically, you're increasing vasoconstriction to increase flow. If you do it locally, you're increasing vasoconstriction to decrease flow. Does that make sense? Okay, sit there with it. If you need to ask a question in a second, you can. People have a little trouble with that one. It just depends on whether it's local or systemic. Okay, so we saw that there were three potential ways to manipulate resistance. There was viscosity, there was like vessel length, and there was vessel diameter. But the only one that we really use on a daily basis is vessel diameter. Okay, so let's back up and reiterate it one more time. There are three ways to manipulate pressure with the delta P, and they are what? Heart, kidneys, vessels. And there's really one daily way to manipulate resistance, and it is vessels. Got it? Okay. All right. So now we are going to talk about cardiac muscle tissue, and I'll tell you a couple of little things about it, and then what we're really going to do is we learn skeletal muscle action potentials and skeletal muscle contraction in excruciating detail, because now cardiac muscle will be easy. Because now all you have to do is learn a couple of little exceptions to how cardiac muscle works compared to skeletal muscle. Okay? So we front-loaded that information so that today wouldn't be as hard for you. So first, before we get into that, let's talk about cardiac muscle actually has the capacity to release another hormone. And I know you wanted one more hormone to add to your hormone chart. Now you got one. Okay? Here is another hormone. It is released from cardiac muscle. And it's called atrial natriuretic peptide or protein or sometimes factor, but it's always AN, ANP or ANF, okay? The P, the peptide or protein, tells you what its chemical category is, so that's cool, right? Now let's break down the name a little bit. Atrial, because that's where it generally comes from, okay? Natriuretic, doesn't tell you, but it implies where it's going. Kidneys, yes. Okay, and now I'm going to tell you why it's released, and because you guys are brilliant endocrine students, you are going to tell me the impact. It is released generally in response to prolonged atrial wall stretching, which might be an indication of what blood pressure? High blood pressure. And what do you think it targets the kidneys to do? Decrease blood pressure by making you pee. Yes? And you pee out sodium and water. Does that make sense? Okay. So, it's one of the few blood pressure reducing hormones. It's the only one that you guys know, actually, or will learn. Okay, so last little bit here before we get into the actual cells is to talk about the metabolism. So for instance, if we want to talk about cardiac muscle cell metabolism, you guys remember what cardiac muscle cells look like, right? So now what do they need in order to function? So the brain, remember, was super pissy about nutrients. It really only likes glucose. It'll burn other things in a pinch, but it prefers glucose. And it really always needs oxygen, no anaerobic respiration to speak of in the brain. Now, cardiac muscle is a little different. It's pretty much a generalist about the nutrient that it'll burn. Like it'll burn almost any sugar you got, but it'll also burn fatty acids and lactic acid. So it's not particularly picky about that. But it has almost zero capacity for anaerobic cellular respiration, which means it always needs what? Oxygen, exactly. So the heart is, fancy way to say it, intolerant of ischemia, and ischemia means reduced blood flow. It will get pissed off. It will first hurt, right? And then later on, it will kill you if you do not deliver it adequate blood flow, right? Okay, it'll at least kill some of the cells and have a heart attack, and if it kills enough of them, especially in the left ventricle, you're screwed. Okay, all right. So now what we're going to do is we're going to talk about cardiac muscle cells. First off, there are two different categories of cardiac muscle cells. There's the ones that you learned in anatomy, which are like striated and are stuck together with intercalated discs and have gap junctions and all of that, right? So those are called contractile cells, and they're going to contract when you tell them to. But then there are other cells, and they are pacemaker cells. And the pacemaker cells are sort of collected in a few places in the heart. You've got the SA node and the AV node, and then some bundles and all of that kind of stuff. We'll worry about the specifics later. But for right now, I just want to tell you that those cells are highly specialized cardiac muscle cells that don't contract anymore. They don't have any actin and myosin in them anymore. They're just really specialized so that primarily what they do is they rhythmically flood themselves with positive ions and then pass them through the gap junctions to their contractile neighbors. Flood themselves with positive ions, pass them to their contractile neighbors. Those cells are called pacemaker cells, yeah, or sometimes autorhythmic cells because they automatically generate a rhythm. Does that make sense? They are cardiac muscle cells. They are not nervous cells, okay? And they are different cardiac muscle cells. What's your question about?
Why positive?
Because that's how you depolarize, right? If you flood yourself with sodium or calcium, you depolarize. And what we need is positive ions going to the contractile cells to make them hit an action potential. Does that make sense? No? Huh. Remember how you depolarize with sodium moving in? You could depolarize with a negative moving out, but that's not how it works. Yeah, you can depolarize with a negative moving out. Is that okay? Okay. It's been a little while since we did that. It's all right. Okay, so we are going to talk about those pacemaker cells first. So about 1% of cardiac muscle cells are pacemaker cells. They tend to be clustered in a few places, SA node, AV node, the bundles, but then there's a few of them that are just around. So I want to talk about how those work. So these pacemaker cells right here, what are they going to do? So let's say the SA node. So it's really not very hard. So here's the deal with the process of generating an action potential in a pacemaker cell. What a pacemaker cell does is generate an action potential, repolarize, generate another one. Generate another action potential, repolarize, and generate another one. It does it over and over and over again. And it does it primarily rhythmically based on your dependable sodium concentration gradient. Okay, and you work really hard so that your sodium concentration gradient is 15:1, right? If you have a dependable sodium concentration gradient and a dependable number of channels, then you can pretty much predict how quickly you are going to depolarize. So let's watch what happens. So this is a pacemaker cell action potential. Its action potential is like between 60 and 70, but it's variable because it really never, its resting potential, is between 60 and 70, but it really never stays there. So it's not like it really stays at rest. It just does this over and over again. So it's a variable resting membrane potential around here. Okay, so variable resting membrane potential about minus 60-ish. And here's what happens is there are channels on these cells that are kind of leak channels. They call them funny channels. They ain't that funny. But they're leak channels that under certain circumstances can be closed. That's all you have to know, okay? And they are sodium channels, okay? So here's what's going to happen. If you have sodium, a dependable number of these funny channels, and a dependable sodium concentration gradient, then you are going to have a dependable leak rate, yes? And since you have a dependable leak rate, what's going to happen is the sodium is going to leak in slowly. Potassium channels are closed when this is going on. And then once you hit threshold, which is right here, it's about minus 40 or 50. It says 50 in your book, but most books say 40. It doesn't really matter. Here. Then once you hit threshold, what's going to happen is you're going to open a new kind of channel. And that new kind of channel is called a fast voltage-gated calcium channel. Calcium is positive, so it would still be depolarizing, right? Yeah? Okay, would still be depolarizing. These are fast voltage-gated calcium channels. Why fast? Because we're going to meet slow ones later. Okay, so calcium is going to rush in from the extracellular fluid. So no contraction follows in these cells. What happens is they take all that sodium and calcium that they got and they send it through gap junctions to their friends, the contractile cells. They're going to send it through the gap junctions in the intercalated discs. Yes? That makes sense to you? Okay. And then, of course, they're going to need to repolarize before they can get their next action potential. Does that make sense? Okay, so I want you guys now to tell me how I'm going to repolarize. You don't have to memorize repolarization. You just have to put everything back where you got it, right? Okay, so how am I going to get from here down? First, let's go to this figure and let's label it together. You ready? This is a pacemaker action potential in the pacemaker cells of the cardiac muscle. So first question is here. How do I get from here to here? What kind of channels are involved? Sodium funny channels. You can call them leak channels if you want. They barely started calling them funny channels, and I'm like, I'm still waiting for the punchline. It ain't funny. And then right here, okay, from here to here, what kind of channel is open? Fast, voltage-gated calcium channel. Okay, now let's fix the number. So what do I need to close here? Close the calcium channels, yes? And now get me back to resting. What kind of channels are going to be open down here? Yeah, those are voltage-gated potassium channels. Yes, everybody with me? Okay, but now the number is right, but the ions are in the wrong place. So let's put everything back where it goes. Yes, we don't have to go. No, it's fine. Put everything back where it goes. So I need 2 pumps now. I need my regular pump, which is the sodium potassium pump, and 1 more pump. I need a calcium pump, right? But by the way, I don't really have to pump that much because remember, most of it actually left already. Most of it left through the gap junctions, just not all of it. So I just have to fix what's left in there, right? Is that okay? Okay, everybody all right with that? So those are the pacemaker cells or the autorhythmic cells. Okay, so now what does the sympathetic nervous system do to this? If you are consistently generating your own action potential, then why do you need a sympathetic or a parasympathetic nervous system, and what can it actually do to this system? What it actually does is, okay, let's go and see how it's wired up. Okay, so here's what happens. If you have the sympathetic nervous system right here coming from the thoracic region of the spinal cord, you guys with me, right? Going to the SA node and the AV node, here's what happens. What it's going to do is it's going to stimulate those pacemaker cells with what neurotransmitter? Norepinephrine, good. It's going to stimulate those cells with norepinephrine. And they were already on their way to depolarization. You just depolarize them slightly faster. So norepinephrine just opens some positive ion channels. That makes sense? So instead of hitting it every 100 times per minute, right, you're going to hit it 105 times per minute. Yeah? Does that make sense? Okay. Would it work if the SA node wasn't already generating an action potential? No. The SA node, your autorhythmic cells, are the starter on your heart. And you can push the gas pedal all you want, but if the starter isn't initiated, you have no functionality of the engine. Does that make sense? Okay. Now, what about the parasympathetic nervous system? It goes to the SA node, the AV node, and releases what neurotransmitter? Acetylcholine, good, okay. And what it does is you're on your way to a depolarization, and what it does is, as you're on your way to a depolarization, it slightly hyperpolarizes by, for instance, opening a potassium channel. And so you just don't get there as quickly. So if you, right now, what you're doing is your parasympathetic nervous system is telling your heart, you don't need to beat 100 times per minute. So it's actually slowing it down to 70 or 60, or what's yours, Boris, right now? What is it? Mine usually is around 65, 67. 72. It's fun. Caffeine increases your heart rate, by the way. Okay, everybody okay with that? Okay, so that's what it does. And the sympathetic and the parasympathetic can't do a damn thing to start or stop your heart. Just imagine that they are the gas pedal and the brake, right? But you have to get the thing started first, okay? All right, so now let's talk about the contractile cells, right? So now what we did is we flooded the SA node, the pacemaker cells, with sodium and calcium, right? And now what I'm going to do is I'm going to send that sodium and calcium through these gap junctions to the contractile cells, okay? So instead of using a neuromuscular junction on cardiac muscle to start an action potential, I'm going to use gap junctions from the neighbors to start an action potential. It doesn't matter how the positive ion gets there, right? Just that it gets there, okay? And then we'll get an action potential and we'll get contraction. So first thing is let's look at the graph and then we'll look at the activity. All right, so this is a contractile cell. And so what happens is it goes from a resting membrane potential about negative 90 and it gets flooded really quickly, right? So what happens here is this depolarization caused by an action potential. So let's talk about how that occurs. So the depolarizing stimulus is the sodium and the calcium that comes through the gap junctions from the pacemaker cells. And those will cause a new kind of channel to open. And these are called fast voltage gated sodium channels. And the fast voltage gated sodium channels are going to go all the way up past 0. That make sense? Okay. So you depolarize and you hit fast voltage gated sodium channels opening. And that's what gets you your action potential. Okay. So I have an action potential. And now let's see what's going to happen on the muscle cell before we finish the rest of the graph. And then we'll label the graph. Everybody ready? Okay. So this looks really similar to the one that you looked at in skeletal muscle, correct? Do you remember the one that you looked at in skeletal muscle? Only no neuromuscular junction, right? Okay, and it's got gap junctions that you're dealing with here. So how do you start the whole thing? You flood this cell, which is a contractile cell. This is, let's say this one's a pacemaker cell, although it could get it from another contractile cell, FYI. They are actually attached to one another. But let's say this is a pacemaker cell. It's going to flood this contractile cell with sodium and calcium, which will depolarize it, right? If you hit threshold, then what's going to happen is you're going to start an action potential. Action potential is going to go along the sarcolemma and down the T-tubules, just like you'd expect it to. But on its way, it's actually got a new kind of channel that it's going to activate. And that is called a slow voltage-gated calcium channel. Why slow? Because it's the second one that actually opens. The fast voltage-gated sodium channel opened first, and then the slow voltage-gated calcium channel. So I want to see what that does to the graph. Okay, do you see what happened? This was a fast voltage gated sodium channel. And then you do a little bit of repolarization as you're going down your action potential, but then you have a plateau in which you stay in an action potential for a while. That's because this is the slow voltage gated calcium channel. That's opening. Why? What it's going to do is it's going to allow for your action potential to be really long and really strong, and then your contraction is going to be really long and really strong. Because when you contract cardiac muscle, do you want it to do this? Or do you want it to be strong or stronger, right? You don't ever want it to fart around, right? You want a decent cardiac muscle contraction, always. You can want it stronger when you're exercising, but you never want it to be a little bitty wimpy contraction. Okay, so let's see what's going to happen here. This is voltage-gated calcium channels opening. We'll do this part in just a second. Let's go back to the cell and see what happens. So now I want you guys to see that I'm going to have a long action potential, but I'm also going to have a really strong contraction as long as I have ATP. Because now, okay, action potential started, then went down the T-tubules, opened the voltage-gated calcium channel as it did, okay? And then as it goes down the T-tubules, it does what you'd expect it to do. It causes calcium release from the SR, right? But now, see, I have calcium from 3 sources. I have calcium that came through the gap junction. I have calcium from the extracellular fluid. I have calcium from the SR. All of that calcium is going to go and bind to what protein? Troponin, move tropomyosin out of the way, and you will do hella cross-bridge cycling as long as you have ATP. Does that make sense? So you don't get any wimpy contraction when you get a cardiac muscle action potential. You get a badass contraction. Does that make sense? Everybody good with that? Okay, so you got 3 sources of calcium as long as you have ATP. And you're going to have ATP as long as you have oxygen, right? Okay, so the original stimulus caused the opening of slow voltage-gated calcium channels during the action potential. Calcium is now in the sarcoplasm from 3 different sources. And so now let's label this and then figure out how you repolarize. You ready? Okay. So I go from a resting membrane potential of around minus 90 or minus 100 to an action potential really quickly, because what kind of channels open right here? Fast voltage-gated sodium channels. Got it? Okay. And then what happens here to allow my action potential to continue? Slow voltage-gated calcium channels. Good? Okay. How do you guys think we get from here to here? How do I repolarize back down to resting? Same way you always do. Close everything right here, right? And then open what? Open voltage-gated potassium channels. Good? Okay. Now I have to put everything back where I got it. You don't have to memorize it. Just figure it out. You don't have to go back through the gap junctions. That's the only thing that you don't have to do. Everything else you have to put back where you got it. So you're going to need 3 pumps, guys. What's the first one? You always need this one. Sodium potassium pump. And then I'm going to need 2 other pumps. Calcium pumps where? Where do I need them? 2 places. SR, calcium pump, pumping it back into the SR, and where else? Cell membrane, yeah, cell membrane, a calcium pump. Does that make sense? Got it? So for me, if I know where it came from, I know how to repolarize, right? If you think through it, you can figure that out. You have to put it back where it came from. Is everybody okay with that? Okay, so let's talk about, here's your pumps, by the way. Here's your calcium pump, calcium pump. This uses a sodium potassium pump and a sodium calcium pump, but you don't have to know about the sodium calcium pump. I don't care. Okay, so interactive physiology. I'm going to tell you, over the weekend, as you are studying, and you should be studying cardiovascular system, interactive physiology is phenomenal for cardiovascular system. It is so good. You can attach the sympathetic nervous system. You can turn things up. You can turn things down. You can decrease calcium concentrations and see what happens. So I would practice. Specifically, I always tell you which pages to use. I don't know how often. Are any of you guys actually using this? No? You should be using it. Nobody? Huh? You use it? You too use it? It's good, isn't it? Yeah, it's actually really good. And it's kind of hard. It's actually not always really easy. So if you don't use it, that's fine, right? I gave you free access to it on the web page. I don't know what the hell to do for you people. Okay, so now let's talk about refractory period. Here's something really interesting with cardiac muscle. Do I ever want my cardiac muscle to go into tetanic contraction? Hell no, I don't. Why not? Couple of reasons. Well, you would die is the big reason, but why would you die is the question. If your cardiac muscle goes into tetanic contraction, right? So we know that your cardiac muscle can beat slowly, it can be in between, you can go into tachycardia in which your heart is really beating quickly. But even tachycardia is not tetanic contraction. So with tetanic contraction, what happens is, and you can't release, right? So you don't want that because, of course, if you do that, you're not filling, right? Your ventricles are not filling when they're contracted. And then there's another reason. Relaxation is just as important as contraction with the heart, because 2 things happen when your heart is relaxed. First, of course, your heart fills only when it's relaxed. And then this other thing that took me an embarrassingly long time to understand, but really helps me now, is that when cardiac muscle is contracted, you're not actually delivering blood to capillary beds, because I want you to think about this for just a second. So stick with me and think about the left ventricle. Left ventricle pumps and pushes blood into the aorta, yes? Do you guys remember that the first 2 branches of the aorta are the coronary arteries? Yeah? So I was confused for an embarrassingly long time. I could never figure out why the hell the heart can be full of blood and you could have a damn heart attack because it didn't have enough blood. I'm like, what the hell? It's right there. Because the blood that is in the heart chambers does not actually deliver blood to the heart muscle, right? It has to go out and then in from the coronary arteries. You guys with that? Okay, so with that in mind, what you do when the left ventricle contracts is you push blood into the aorta and the coronary arteries, but simultaneously you're compressing the capillaries of the heart. Yes? So you're getting it into the arteries. When does it get into the capillaries? Well, it's like squishing a sponge underwater. When do you actually take up the water? When you relax. Exactly. So here's the deal. If your cardiac muscle is contracting and contracting and contracting, you are actually cutting off blood flow to the cardiac muscle cells, right? So you need to relax the heart, not just to fill the ventricles, but also to deliver blood to the myocardial capillaries. So you will see that in a healthy person, as we go through this, your heart spends almost equal proportions of time, 50-50, relaxed and contracted, relaxed and contracted. Even as you go faster, it's still about 50-50, relaxed and contracted. Okay, so your heart, in order to avoid tetanic contraction, really controls the refractory period. Remember, the refractory period is the time when the voltage-gated channels haven't reset, so you can't have another action potential. If you make the refractory period super duper long, you can't get tetany, right? Because you can't get summation. So what's the refractory period in cardiac muscle? It's pretty damn long. So in skeletal muscle, it's pretty short. It's even shorter in neurons. But in skeletal muscles, it's 1 to 2 milliseconds. But in cardiac muscle, it's 250 milliseconds. And that will take care of any possibility of summation. You're like, I'm trying. You're like, I am still busy with this last one. So a long, strong action potential with a long refractory period gets you a long, strong contraction that can't be added to another contraction, right? So each contraction is individual because it takes a long time to reset. Is that okay? Okay, so that's the refractory period. It's an absolute refractory period. Okay, everybody all right? Do we need to have questions?
Can you draw that?
Can I draw? No. That's a good challenge that I would work up to, but I don't think I can do it right now. Draw what would be happening with the absolute refractory. I'll think about it. If I can come up with a way to communicate it, I'll do it on Monday or Tuesday. Okay. Okay. So now I want to talk about something that's directly related to this. Okay, because this is the point of it all, right? Blood flow, and it's called cardiac output, abbreviated CO. Okay. So we know that you can control pressure and therefore flow with what your heart does, what your vessels do, and what your kidneys do. I'm going to concentrate on what your heart does for a minute, okay? So specifically, we are going to refer to this as cardiac output. And cardiac output is the amount of blood that leaves a ventricle per unit of time, okay? And we're going to concentrate on the left ventricle because of systemic circulation. You could do the same thing with the right ventricle, okay? And cardiac output is pretty easy to understand. It's going to also be measured in unit of volume per unit of time, usually liters per minute. You can do milliliters if you want to. Okay. So what we're going to do is we are going to look at cardiac output and realize, just conceptually, that cardiac output is, of course, going to be one of the big determinants of pressure, right, and therefore flow. One of them, not all of them, but one of them. Yeah. Okay. So cardiac output is the amount of blood that is ejected from a ventricle per unit of time. Let's keep it at a minute. And it's pretty easy to understand because it is simply how many times you contract per unit of time multiplied by how much leaves per contraction. Yeah? So it's heart rate times stroke volume equals cardiac output. Yes? So if I needed a greater cardiac output, like if I was working out, I could manipulate this one, that one, or both of them. Yeah? Okay. And if one of them is compromised, let's say I'm having a heart attack, yes? Having a heart attack, which one would be immediately compromised? Stroke volume, right? Okay. And I would try to compensate by increasing my heart rate, if I could, right? If my heart rate was the problem, I would try to compensate if I could by increasing my stroke volume. This one's harder to increase. Are we okay with that? Go ahead.
Does the heart not have an upper limit where it will stop?
It has, no, it doesn't have an upper limit where it will stop. It has an upper limit where it will stop being able to deliver blood to itself, and then it will have a heart attack. But you can go up to like 260, 270 beats per minute before you die. And then you will die, unless somebody fixes it. Yeah. So you can really, really be super duper tachycardic, and they will know that you're about to die unless they actually do something. And specifically, you're about to die because when it's doing that, it's not filling, it's not delivering blood to the myocardium, and it's not delivering blood to your brain. And so you're going to die of a heart attack or a stroke. Go ahead.
I got to work on the telemetry for the IMC.
Uh-huh.
So one of my friends was telecertified when we were talking about it one time. He's like, if your heart rate, there's like two conditions. Let's say if your heart rate is like above 250,
Uh-huh.
or you're not completely, I forgot what the QRS weight is
Mhm.
all showing, you will die probably in about 15
15 to 20
to 20 minutes.
minutes, that's a long time.
Or something like that. You won't get to live.
You're definitely gonna die.
Yeah.
Yeah.
It's like if they see that pattern.
Well, they're probably gonna cardiovert, right? Either chemically or something. Yeah. There's some chemicals now. I don't know how they work. I need to teach myself. They're new, relatively new chemicals that they can use for cardioversion before they actually use the paddles. I don't know how they work. I'm super curious, but apparently not curious that I've looked them up yet. I will. Okay, so let's look at an average cardiac output of a regular person at rest. This is just an example, okay? So this is a regular person at rest within a normal heart rate range and within a normal stroke volume range, okay? So an adult example, a stroke volume, a not unusual stroke volume is around a quarter cup or 7/100ths of a liter. So a quarter cup per squirt, and a heart rate among normal, 72 beats per minute, which is what Boris's is right now, okay? That's among normal. And you can go way, way lower than that. You can go higher than that. So that means that the cardiac output of this person at rest ends up averaging out to about 5 liters per minute, which is pretty damn impressive because how much blood do you have? You got about 5 liters. If you're bigger, you probably have a little bit more. This means you pump your entire blood volume at rest every minute. And then you can go higher than that, right? You can go way higher than that. So with that in mind, we should probably treat our heart a little better. Instead of having in and out today, you should probably have a little kale. I've tried to sneak kale into my family's food all the time, and they're like, ew! I feel the same way about kale. I hate it. It's one of those things that I should probably like. It's gross. Okay, so each of these factors is pretty complicated and has a bunch of regulatory mechanisms, but they're all pretty logical. So there is a phenomenal introduction to cardiac output and interactive physiology, which apparently only 2 of you are going to use, but that's fine. Maybe these 2 will get better grades, and then they were going to go neener. Okay. But what I'm going to do is I'm going to start by looking at stroke volume, because we already know a lot about heart rate, right? We already know that the primary ways that you regulate heart rate is with the sympathetic and the parasympathetic nervous system. And then we're also going to have some hormones that can regulate heart rate that you might or might not know yet. Everybody okay with that? So we're going to start with stroke volume. Stroke volume is how much you squirt out each time your ventricle contracts, okay? So there are some factors that regulate stroke volume. And I want you to listen to these carefully because the words get confusing. The ideas are not confusing. Okay, actually, I don't think they're very confusing. Okay, but the words are definitely potentially confusing. So I want to talk about the factors that are impacting stroke volume. So here we go. Here's stroke volume. This is how much leaves per squirt, and we're going to start with this one. Okay, all right. So the first concept is if we are looking at stroke volume and we consider our ventricle P1, right, and our arteries P2, right, then we want blood to go that way, right? We always need arterial pressure to be lower than ventricular pressure. Yes? You with me? Okay. So what I want to know is what will happen to stroke volume as arterial pressure increases and ventricular pressure stays the same. That concept is called afterload, because this is before and this is after, right? Before is in the heart, after is in the arteries, after arteries. Make sense? Okay. So I want to know what is going to happen to stroke volume if the pressure in my arteries increases with, for instance, vasoconstriction or arteriosclerosis. Okay? So what is going to happen to my stroke volume if my afterload, the pressure in my arteries, increases? Is it going to decrease or increase stroke volume? Let's think about it. The arterial pressure against which the ventricles are pumping, the P2 increases, right? My P2 increases, and now it's 85 instead of 70, okay? And increased arterial pressure tends to do what, Abel, to stroke volume? Decrease stroke volume, yes. And let's just think about this. Now, I've got a person who has decreased stroke volume, but they need the same cardiac output because they need the same blood flow to their capillary beds. What do they do to compensate? Increase your heart rate. Yes? Okay. That is the story that starts with hypertension, right? You get arteriosclerosis. You get cholesterol, high cholesterol first, right? It's usually the first indication before you even have arteriosclerosis. And then you have arteriosclerosis, and then you have hypertension, and then your heart rate goes up, right? And and it all happens like this. And why? Why are you trashing the system? Because the overarching functionality of the cardiovascular system is to ensure adequate blood flow to capillary beds. And if you mess with the tubes, the pump has to compensate. Does that make sense to you guys? Okay, so that's called afterload. And so the relationship between afterload and stroke volume is this. If you decrease afterload, you increase stroke volume, or the opposite, right? If you increase afterload, you decrease stroke volume, right? It's a inverse relationship. Okay, everybody all right with afterload? Afterload arteries, okay? Now, stroke volume is also impacted dramatically by what we call EDV, which is this guy right here, end diastolic ventricular volume, okay? So I want to break that down, okay? So end diastolic ventricular volume, abbreviated EDV. So what I'm talking about is the volume in the ventricles at the end of diastole. The end of diastole is right before systole. Yes, right before contraction or systole. When should the ventricles be fullest? Is that a word? Most fullest, more fuller. So when should they be the most full? Right at the end of diastole. That's a good indicator of how much you're going to squirt out, which is how much you have in there right before you contract, right? But I want you to understand that it has to do with the volume of fluid and also the fact that the container can be full or fuller because it's a stretchy container. Yes? So the volume of fluid and the volume of the container, you guys with me? So that is called end diastolic ventricular volume. And so before we get into the details of end diastolic ventricular volume, let's just see the prediction. Stroke volume is affected dramatically by end diastolic ventricular volume, the volume of the ventricles just before the contraction at the end of diastole. So what's your prediction? Increased EDV tends to do what to stroke volume? Increased stroke volume. Yes, of course. Here is increased EDV, and that increases stroke volume. Does that make sense? So now all we need to do is figure out how you increase EDV, and there's a couple of different ways. Everybody okay? So the question I'm asking you is, how do you make the ventricle full or fuller, right? How do you do that? Okay? So primarily it's got to do with how much blood is coming back to the atria and then is pumped into the ventricle, right? How much is coming back to the atria and then is swished into the ventricle. Is that okay? Okay? Is that conceptually okay? Okay. So what is in the ventricle has primarily to do with the back end of circulation, not the front end of circulation. Got it? Okay. Do you know the term venous return? Do you know that term? Venous return is how much blood is actually coming through the veins, coming back to the atrium, and then into the ventricle. So keep venous return in mind as we're talking about this. Okay, let's look at the factors that impact EDV. These should be logical, but the words are hairy, so make sure you get the words down. Okay, the first one is basically this concept of the amount of tension. This is called preload. Preload happens in the ventricles, afterload happens in the arteries. Pre-after. Does that make sense? Okay, so preload is the amount of tension in the cardiac muscle cells of the ventricles just before they contract. And so preload is really impacting how full is your ventricle, right? How full your ventricle is has to do with how much fluid is in there and how stretched it is. Okay, and that is going to be impacted by how much time you give it to fill. Okay, filling time. Okay, filling time is dependent on heart rate. So here's the deal. Let's look up here for a second. Can heart rate be so fast that you don't have enough time for filling? So there's a sweet spot here. Yeah, there is a sweet spot. If it's super, super fast, you won't have enough filling time. So basically, here's the relationship between heart rate. So as heart rate decreases, as long as you are decreasing within the normal range, you can get so slow you're going to die. But if you're decreasing within the normal range, then filling time and stroke volume can increase. Let's talk about Lance Armstrong for a second. Lance Armstrong, in his prime, despite the fact that he decided to do some drugs, was also an amazing cardiovascular specimen. Okay? Amazing cardiovascular specimen. In his prime, at rest, his heart rate was around 37 beats per minute. What does that mean? That means that his stroke volume was freaking enormous. His heart rate was super duper low because his stroke volume was so very high. Was that healthy? Hell yeah. He could live forever, especially since he had one less testicle to pump to, right? So if you had to choose which one to bump up to maintain the health of the system over time, keeping your stroke volume really high can keep your heart rate really low, and basically you're wearing out your machinery far less than the rest of us. So if you're a really good cardiovascular athlete, your resting heart rate can be in the 60s, the 50s, the 40s. I don't know anybody else who had it in the 30s, but there probably are some Olympic athletes who are in the 30s, especially cardiovascular athletes, right? Not like a skeet shooter or something. Okay. So does that make sense? So filling time, go ahead.
So when you're doing cardiovascular training, what are you training your heart to do?
You're training your heart's efficiency. That's what you're doing. You're actually making each stroke stronger by actually training your heart to do stronger contractions, so they have to do less frequent contractions. Simultaneously, you're also cleaning out your blood vessels so your afterload drops. Yes? And so you get the double whammy for cardiovascular exercise, right? You're decreasing your afterload and increasing your preload with cardiovascular exercise. Good? Okay, so the other thing that matters, okay, so we've got the filling time, and then we have the concept of atrial pressure. And the atrial pressure is, okay, what's happening in the atria that determines what's going to happen in the ventricles? Okay, this is pretty logical. How full your atria are determines what's going to go in your ventricles. And then also how strongly your atria contract will determine what goes into your ventricles. Does that make sense? So you got your heart rate, and you got your filling time, and you got your atrial pressure. Now, I have atrial fibrillation, okay? So I want you to figure out what happens to my stroke volume when I have a bout of AFib, okay? What happens to my stroke volume? My atria, instead of contracting, they just go. Is blood still going into my ventricles? It is, but only about 80% of the blood that would normally be going into my ventricles. So let's look at what happens with me with atrial fibrillation. What happens is I go into atrial fibrillation, and it starts, and one time it lasts for like 18 hours. So my stroke volume drops really, really low. What happens to my heart rate? It goes up really, really high to compensate because I have to deliver adequate blood flow to capillaries, right? And that's that whole atrial pressure. I am compromising atrial pressure, which drops my stroke volume. Does that make sense to you guys? Okay. So if I ever pass out in front of you, which has happened once in the 14 years I've been here, that's what it is. It's atrial fibrillation. Just don't let me crack my head open because I've already done that once. Okay. So everybody all right? Okay. So what we have is EDV, and now we are going to talk about Starling's law. And this one can confuse the hell out of you unless you give it a second. So stick with me. There is this natural mechanism in the heart that allows it to contract harder when it's fuller, that has to do with just how the sarcomeres are stretched in the cardiac muscle. So here's the deal. As venous return, right, increases, what should happen is my ventricles should contract harder. Yes? That's what should happen. Now, there is a natural mechanism in the heart that makes that happen that doesn't have anything to do with paracrine agents, doesn't have anything to do with neurotransmitters or hormones. It's just this natural mechanics of the heart. It's called Starling's law. And here is how Starling's law works. Starling's law says that if I increase my ADV, then what happens is my cardiac muscle sarcomeres get stretched to a more optimal length and have more options for cross-bridge cycling. Yes? And since they can actually do more cross-bridge cycling, you actually naturally get a stronger contraction. So here is sort of a full heart, and here's what your sarcomere looks like. And you get cross-bridge cycling, right? You get some. But it actually works better when it's stretched more. Yes? Okay? And this is called Starling's law, and it basically says that as venous return changes, the heart automatically adjusts output to match inflow. So when does your heart contract best? When it's fullest, if you're healthy. Okay? Does that make sense? Okay? So this is increased venous return, like when you're exercising. When you are exercising, your heart actually has better stroke volume because of this. Stretches the muscle fibers in the heart wall, and the muscle fiber sarcomere length is more optimal than at rest. And this venous return, let's talk about how you actually get this venous return. So this is something that conceptually is a little confusing to people. When I'm exercising, what happens is We know that my heart is, of course, increasing, and we, of course, know that arterial circulation is going to be far more because of what my heart is doing, but that doesn't directly impact venous return. What the heart is doing is not directly impacting venous return. Venous return is how quickly the blood is moving back to the heart. And it's really on the other side of the capillary bed, and it doesn't even have any pulse pressure, right? So what the hell about exercising actually increases venous return? Well, two things. What we call the skeletal muscle pump. And the skeletal muscle pump says, okay, arteries do what the heart tells them to. Veins, you have to do something else. With veins, what primarily impacts venous return is skeletal muscle contraction pushes on veins, and most of your veins have valves in them, so if you push on them, it actually makes blood go unidirectionally but more quickly. That's called the skeletal muscle pump. Does that make sense? And then there is also the respiratory pump. Have you guys heard of the respiratory pump? Okay, the respiratory pump is super cool. So the way the respiratory pump works is, so I've got my diaphragm, yeah? And my diaphragm separates my thoracic cavity from my abdominal pelvic cavity. And of course, there's a boatload of blood vessels, including the inferior vena cava that goes up through there. Continuous to superior vena cava, a whole bunch of blood vessels. All of these vessels in the entire ventral body cavity have no valves in them because they don't need them, because you breathe pretty damn dependably. Here's what happens when you breathe. When you breathe, the diaphragm goes from being this shape, squishes down. What happens to the pressure here? Increases. What happens to the pressure here? Decreases. And you squirt blood up all of those blood vessels and up your inferior vena cava every damn time you inhale. And when you are exercising, how much more frequently and more deeply do you inhale? Yeah. So it actually aids in venous return. That's a relationship of exercise to venous return, the skeletal muscle pump and the respiratory pump. Is that okay? Okay. So that's the skeletal muscle pump and the respiratory pump. Okay. So last little tidbit is giving us some encouragement, which we all need to do cardiovascular exercise. Some people like it. It makes them release dopamine. I envy you because I just sit there the whole damn time and think, I wish I was reading a book. Honestly, it sucks. I did buy one of those climber things at home. I totally love that thing. Those things are awesome. They're so hard. I was like, I'm going to do 30 minutes a day. I was like, oh my God, I'm going to do 8 minutes. And my husband can't even do 4. So, stretching will cause the force of contraction to increase and more blood is going to be ejected. So what I want to talk about, just the last thing, is exercise will increase your stroke volume, which allows for your heart rate to decrease. And this is good for the long-term health of the system, right? Totally good for the long-term health of the system. You're using it less frequently but more efficiently, and that's good for any machine, right? So what I want to talk about is cardiac reserve. Cardiac reserve is how much you can do above your resting rate. And this is really interesting because I want to talk about Lance Armstrong again for a second. Lance Armstrong's resting heart rate is 37 beats per minute. But can his heart rate go above 200? It totally can. So his cardiac reserve goes from 37 to 200 beats per minute. Now, when he gets up to 200, his stroke volume is compromised. But he's still got a tremendous capacity to increase his blood flow above what his resting is. And cardiovascular exercise increases your cardiac reserve, is what it does. It increases the amount that you can do above resting. So you decrease heart rate, increase stroke volume, and you can still go up to the highest heart rate. And so if you're in really, really good cardiovascular condition, you've got a really broad cardiac reserve that you can go up to, right? And it's something to work toward. Does that make sense? Okay, so I'm going to reiterate what I want for you guys to do this weekend. I am going to post for you a 20-25 minute prep yourself video that goes through some of the stuff we did before and some of the stuff we're going to do next time. It's going to include a big complicated concept map. Have you guys ever used concept maps? Cardiovascular system? Don't use it if you hate it, but it's a really good way to organize all the cardiovascular information. And I will give you the concept map and then work through it in the video, right? It's going to talk about all the stuff that we're going to do on Tuesday. If I were you, I would look through all the questions in the quiz before Tuesday to see if you can field them and which ones you don't understand, and then come back with questions. And then we're going to get through as much as we can on Tuesday. If we don't finish the last little part of it, we'll just roll it over to test 4. Okay? All right, so you got a quiz. Your quiz is not due Thursday, it's due Wednesday. So make sure you do it before Wednesday, okay? Okay.